Welcome back to our chemistry flipped classroom, and today we're continuing our discussion around equilibrium. And so we're going to continue discussing the equilibrium constant, or K. So just a quick review of what we already know about the equilibrium constant. We know that the equilibrium constant is equal to the product of the concentrations of the products raised to their coefficients divided by the product of the concentrations of the reactants raised to their coefficients. So in this example, where we have our nitrogen dioxide decomposing into nitrogen monoxide and oxygen gas, we would have nitrogen monoxide raised to the second power, because we have a coefficient of 2, times the concentration of oxygen raised to the first power, divided by nitrogen dioxide raised to the second power. So it would look like this. And remember, we use the square brackets to indicate that these are concentrations. The 2 is from the coefficient, a 1 here as a coefficient, and again, a 2 here as a coefficient. And it's always products over reactants. Okay. So with that said, there are a few times when there might be things that we leave out. So I want you guys to think about a situation that happens to us occasionally. So let's say that the cafeteria is all out of sweet tea and you really wanted sweet tea with lunch today. And so you pour sugar into your tea and you stir and stir and stir and stir and stir. And some of the sugar dissolves and some falls to the bottom of your glass in a heap. And you can add more sugar, but it's still just going to fall to the bottom of the glass in a heap. So our aqueous sugar and our solid sugar are in equilibrium. And so no matter how much more sugar you add, no more dissolves into your glass, and you're frustrated and left with a sugary pile at the bottom and not sweet tea on the top. And so this is what we call a heterogeneous equilibrium. So heterogeneous equilibrium is when you have an equilibrium situation where not all of the species, not all of the substances are in the same state of matter. And so a heterogeneous equilibrium might have liquids and aqueous solutions, or it might have solids and aqueous solutions. It might have solids and gases, or even liquids and gases. But when we have a heterogeneous equilibrium, those pure solids, they don't affect the position of equilibrium. Doesn't matter how much more sugar you add to the glass, no more sugar is going to dissolve. We're just going to make the pile of sugar at the bottom bigger. In the same way, a pure liquid does not affect a heterogeneous equilibrium. And one way to think about this is that we really can't measure the concentration of a pure liquid or the concentration of a pure solid. And so it's almost like they have infinite concentrations and they don't affect the equilibrium. So that means that when we write the K expression for a heterogeneous equilibrium, we do not include anything that is a pure solid or a pure liquid in the expression. So if we're looking at this expression, we have our solid phosphorus pentachloride decomposing into liquid phosphorus trichloride and gaseous chlorine. So here we have a heterogeneous equilibrium. We know it's an equilibrium. We have the double-headed arrow. We have a solid, a liquid, and a gas. And so because we have a pure solid and a pure liquid, we know that we're not going to include those in our equilibrium expression, or our K expression. And so our K is just going to equal the concentration of the chlorine gas. So leave out the liquids, leave out the pure solids. Okay, so what can we do with K? Now that we know how to write K, what can we do with it? Well, if we know the concentrations of the species at equilibrium, we can calculate K. So we're given a reaction here. Hydrogen and sulfur form hydrogen sulfide gas, and it tells us the concentration of hydrogen sulfide gas, and it tells us the concentration of hydrogen, and it asks us to calculate the equilibrium K, the equilibrium expression. So the first thing we're going to have to do is write the chemical equation, the equilibrium equation, which is a pretty easy one this time. Hydrogen gas plus solid sulfur makes hydrogen sulfide gas. It's already balanced, but notice that it has become very important, again, to always include the states of matter. So our K expression here, our equilibrium expression, is going to be the concentration of hydrogen sulfide divided by the concentration of hydrogen. Because sulfur is a solid, we're not going to include it, and that's why we're not given the information in the problem. So having written our K expression, we can now plug in these values, the 0.0135 molar for the hydrogen sulfide and the 0.198 molar for hydrogen gas, and we can solve for K, and it's 0.0681. Now notice that K in this case is unitless. We don't have to worry about the units of K. Okay, so that's one way that we can use K. Another way that we can use K is that if we're given K and at least some of the concentrations, we can figure out the concentrations of everything else. So if we know K and the concentrations of some species at equilibrium, we can figure out the concentrations of the other species at equilibrium. So as an example, the concentration of hydronium ion and acetate ion at equilibrium is 5.2 times 10 to the negative third molar. And we're given the KEQ of the dissociation reaction, 1.8 times 10 to the negative fifth, and we're asked to find the concentration of the acetic acid. So we know this is a dissociation reaction. So our reaction begins with acetic acid and water, and we have the hydronium ion and the acetate ion. So we have an aqueous species, a pure liquid, and two more aqueous species. So our equilibrium expression is going to be the hydronium ion concentration times the acetate ion concentration divided by the acetic acid concentration. And because water is a pure liquid, it does not appear in this expression. And now in order to find the concentration of the acetic acid, which is down here, we're going to plug in the K value and the two concentrations that we know, the concentration of hydronium ion and the concentration of acetate ion, which are the same. And we're going to divide by the unknown, the acetic acid concentration. So then we're going to have 5.2 times 10 to the third times 5.2 times 10 to the third divided by acetic acid concentration equals 1.5 times 10 to the negative 8. And so we're going to solve for the acetic acid concentration, and we get that it is 1.5 molar. So if we're given concentrations, we can find K. If we're given K and some of the concentrations, we can find the concentrations of all of the species. And then the one last thing that we're going to talk about with applying K today is that we can look at the value of K and we can determine whether there's going to be more product at equilibrium or more reactant at equilibrium. So let's just go ahead and look at this one as an example. And we can see that K is a very small number, 1.8 times 10 to the negative fifth. And when K is a very small number, well, because this is our K expression, if it's a very small number, that must mean that the denominator of the fraction is much larger than the numerator of the fraction. So that means that I have more reactant than product when K is a small number. And when we talk about small number, we mean less than 1, because if there's more, if the denominator is larger, then we're going to have a number that's less than 1. So when we have a very small K, then that means that we have more reactants than products, and we call that situation reactant favored. So when we're at equilibrium, very little of our reactant has been transformed into product. So if we go back and take a look at this example, you can see that the concentrations of the products are 5.2 times 10 to the negative third molar. but the concentration of the reactant is still 1.5 molar. So there's very, very little of the hydronium ion and the acetate ion as compared to the acetic acid. And this fits with what we've been talking about with weak acids. On the other hand, when we have a large value for K, a value larger than 1, then that means that we have more products than reactants. And so we call that product favored. So what that means is that when we're at equilibrium, there's lots more product than reactant. Most of the reactant has been converted to product. So you should be able to use whether the value of K is greater than 1 or less than 1. So whether the value of K is large or small to determine the relative concentrations of products and reactants at equilibrium. If it's greater than 1, we have more products than reactants. If it's less than 1, we have more reactants than products. So as always, let me know if you have questions, and I will see you soon.